Alrighty, everyone. So, this is the last part of this unit, but you are going to be going back and doing topic 8.6. So, we are going to be covering multiple topics because they all come together. And really, 8.7 we've actually already talked about quite a bit. pH versus pKa, like we already did that with the half equivalence point. So really the focus is here, and it's all about buffers, okay? Buffer capacities and this equation that we can use when it comes to buffer solutions. So we need to start off by explaining what a buffer solution is. So we are on page 42. Make sure you're following along, taking notes as we go. So buffer solutions are really cool because they resist changes in pH. So it's a combination of two things that when we add even strong acids or strong bases to, for a long time, they will resist any major changes in pH. We've also seen titration curves, and I did see a question on this, so let's talk through this really quick. We know how our titration curves look, where we get little to no, some change in pH, and then we get this huge change in pH, and then it kind of plateaus again. Now, reminder, buffers, their entire purpose is to resist change to pH, okay? Resisting change to pH. So there's two areas we have right here, and we have right here. Okay, these areas are considered buffer regions of a titration curve because the pH is not changing very much. Even though we were adding a whole bunch of base or acid to this, because even though we're added a whole bunch of base, see how we resist a change in pH for such a long period of time, and then all of a sudden we overwhelmed it and we got a big change in pH, and then it was resisting it again. So really this is our buffer area here, where we're adding a strong base, but we were resisting a change in pH. And so there's something that's happening in this area. And the first thing is that we have an acid, and usually for a buffer solution, it's a weak acid. So buffers contain two things. They contain a weak acid, and then they contain the conjugate base of that acid. And that acid conjugate base is usually found in an ionic compound, in a salt. So here's an example. I could make a buffer solution, and this buffer solution could contain a weak acid like acetic acid. So this buffer solution can have CH3COOH in there, aqueous. And then it also needs the conjugate base. So a reminder that acids lose an H+, right? And so then what they turn into is their conjugate base. So if this is the weak acid, this is the strong conjugate base. So I need to, in addition to this weak acid, I need to have a bunch of this conjugate base, and usually it comes in the form of an ionic compound. Let's rewrite this so it's similar to that. What if we take Na, like Na+, and we combine it with that CH3COO minus? That's an ionic compound. That's a salt, right? So we have this plus one, this minus one, right? And so then when they combine to make those this ionic salt. So that would be a great example of two items we could combine together. We could take this weak acid and then a salt that happens to contain the conjugate base in there. And that would be a great buffer, okay? So buffers are a weak acid with its conjugate base, usually combined in an ionic compound. And another place that a buffer can be is a weak base with its conjugate acid, usually in the context of a salt. Okay? So let's do an example of that. What about NH3? Okay, so this is a weak base. And we know bases gain hydrogen, right? So if this is the weak base, aqueous, its conjugate acid would have gained an H+. Okay, so that's its conjugate acid. And so if something contains this ion in there, then those things combined would be a buffer solution. We could go with chlorine, like this could be an ammonium chloride, so we could put this with Cl-, and then the +1 and the -1 cancels, aqueous. So there's another example of a buffer solution. Okay, so it contains either a weak acid or a weak base, and its conjugate acid or base usually combined with a salt, so ionically combined with something. Okay, now, before we continue on, actually, I'm going to insert this right here. Let's talk about why these buffer solutions work. Why is it that they resist these changes? So let's give ourselves a little box here, because I didn't really leave space to go over this. So what's great about a buffer solution is that it contains a weak acid and its conjugate base in the form of a salt. Okay, so if we add an acid or if we add a base, something will address that. So let's say we have some kind of weak acid, HA, some kind of weak acid, and we have an ionic compound that contains its conjugate base, A-. So I noticed a lot of questions that would say, well, what if we have this buffer solution and we add a base to that? Like, let's add a strong base like sodium hydroxide. Well, what is it going to react with? The base is going to react with the acid, not with the conjugate base. So if we take our acid and we have it react with the base, oh, this is a neutralization reaction. We would get water, liquid, and then we would get a salt of some kind. It'd be this Na A item here. It would some kind of salt, right? An ionic compound. And so see how we stay relatively like neutral. Like we're not changing pH drastically because we're creating water and then the salt. Okay. If this breaks apart as well, then this Na plus and this A minus, right? Then the sodium can show up on both sides and it can cancel. So what if they ask you, here's our buffer solution and we're going to add a strong base, and they want to know what the net ionic equation is. So first off, if it's a weak acid, we don't break it apart. Okay, weak acids, we don't break apart when we're doing net ionics. Strong bases, we would break apart. And right away, if it's easier for you, if it's a strong base, you can just include the hydroxide because this is going to cancel with that guy over there. And so then what you're left with is water, liquid, and then this conjugate base. So whenever we have a buffer solution and we add a base to it, it just makes more of this conjugate base that's already in there, already accounted for as far as pH goes, and then water, liquid. All right, what about if we add an acid? Let's add a strong acid, and if it asks for the net ionic, we know with a strong acid, the H plus breaks apart, so you can just do the H plus instead of having the whole thing when it's a strong acid. And now it's going to react with our conjugate base. Well, what would this produce? It would be our weak acid again. And so here we can just see, like, we can produce these net ionics by considering if it's a strong acid or a weak acid. And, sorry, not strong acid or a weak acid. We can consider these net ionics when we are considering if we're adding an acid or a base. This is what you're starting with. You have an acid and you have a conjugate base. And if we add a base then it's going to react with the acid. But if we add an acid, then it's going to react with the conjugate base. Okay, great. This is called the Henderson-Hasselbalch equation, and it's provided for you on your blue reference sheet. It's right down here. So HA is the acid, the concentration of the acid, and A minus is the concentration of the conjugate base. Be mindful that often they give you the concentration of the salt that has the conjugate base, and it's just exactly the same as that. So we have concentration of our acid, concentration of our base, and we take the log of that fraction, and if you add that to the pKa, then you can solve for the pH of these buffer solutions. This also is an equation that works for just weak acids in general. Like if you can solve for the concentrations of these things, plus the log of those concentrations, and then we add that to the pKa, you can get our pH values that way. So when we're looking at this, let me write an equation. So weak acid, we saw this one, we saw HNO2 instead of HNO3, right? And so we have our weak acid here, and its conjugate base is when we lose that H plus. So then our conjugate base would be NO2 minus. So looking at an example here in a little bit, we'd find the concentration of each of those items, and then you can plug it in here. And then if you're given the Ka, you would do the negative log of that to find the pKa. If you are given the pKa, don't change it, right? Like don't change it to Ka, or don't take the negative log of it again. So be really careful about what they're telling you. Did they completely give you Ka, or did they completely give you pKa? Then just put it in the equation. If they gave you Ka, just remember to get pKa, we'll do negative log of that Ka value. Okay? And that's how we can figure out our pH. Now, something that's really cool about this equation. Remember how I told you that at the half equivalence, so here's our equivalence point, right? And something really cool happens at the half equivalence. At the half equivalence, our pH is equal to our pKa. And we've discussed what's also going on with this acid and the conjugate base. Because remember at the very beginning, let's say I have acid at the very beginning, right? At the equivalence point, that acid all of it has become the conjugate base. So this would be my conjugate base. But at the half equivalence, half of the acid has become the conjugate base. So only at the half equivalence does the concentration of the acid equal the concentration of its conjugate base. Okay, so what if these are the same then? We're at the half equivalence point. This is 5 and 5, 10 and 10, whatever, right? Any number over itself is equal to 1. Well, if you plug this in your calculator, you'll see that the log of 1 is 0. And so if this whole thing is 0, at the half equivalence, this whole thing is 0, pH is equal to pKa. And that's why we can make that assumption there. If you notice that your pH value is bigger than your pKa value, then you had more conjugate base than you had acid. If you notice that your pH is smaller than your pKa value, then you had more acid than you did base. That's easy enough for us to follow. Okay, let's do an example. So a buffer solution is created by dissolving 87.5 grams of CH3COO-NA. This is an ionic compound. This is a combination of CH3COO minus and Na plus in 1 liter of 1 molar CH3COO. All right, so we need concentration of the acetic acid, CH3COOH, and that's provided. It's 1 molarity. We also need the concentration of the conjugate base, okay? And then we need the pKa. If we can get these items, then we're going to be able to solve for that pH using that Henderson-Hasselbalch equation. So to get concentration of this, we need moles of the CH3COO minus over the volume total. We already have the volume, it's 1 liter, and we know how many grams of this thing we have, so let's figure out how many moles that is. So if I have 87.5 grams of CH3COO-NA, okay, grams of CH3COO-NA to moles of CH3COO-NA. And then I'm going to go moles of that item, CH3COO-NA, to just moles of the conjugate, CH3COO minus. All right, calculator. So I have 2 carbons in there, 3 hydrogens, 2 oxygens, so 2 carbons plus 3 hydrogens plus 2 oxygens plus sodium. Okay. There is 82.034 grams per mole. And then look at this. See how if I have 1 of these CH3COO-NA, like if I have 1 of those guys, there is 1 CH3COO minus. So it's a 1-to-1, right? Like the moles of one equals the moles of the other. So we're going to take 87.5 divided by our molar mass. So the answer to this goalpost was 1.06, etc. moles of the CH3COO minus. And we're dividing it by 1 liter, so then the concentration equals roughly 1.06 molarity. Okay, so I have 1 and I have a 1.6. I have a longer number. I'm holding on to that longer number. And then they tell us the Ka. All right, I'm going to scoot this guy down here. So pKa is equal to the negative log of that Ka value. So negative log of 1.8 times by 10 to the negative 5th. Okay. Negative log 0.8 times by 10 to the negative 5th. 4.74, etc. And so to solve for the pH, I'm going to take the pKa and I'm going to add it to the log of the conjugate base over the acid, the concentration of the conjugate base over the concentration of the acid. So my final answer, pH, is equal to pKa plus the log of the concentration of CH3COO minus over the concentration of CH3COOH. So this is going to be roughly 4.74 plus the log of, and then the conjugate, 1.06. I'm going to use my long numbers when I do this, over 1. And let's see what we get. Okay. Plus the log of the 1.6 divided by 1, which is just that guy. Okay. My Ka value was 2 sig figs, the grams was 3 sig figs, the volume was 3, but this was 2. Oh, no, but we're, oh, yeah. Man, sig figs are tricky on this one. Here's the idea. So, we're taking log values of this, and so that would mean that the answer to just this part would need multiple digits afterwards, after the decimal. It would be 3 digits after the decimal, where this one, here's our Ka, so we had 2 digits after the decimal as far as sig figs go, and then we're adding them together. So I believe our final answer with sig figs and everything is 4.77. Again, to get you in the best possible answer for sig figs with this Henderson-Hasselbalch equation, look at your Ka value and see that there's 2 significant figures, and then recognize that this is a p value, so the leading digit's not significant, so then we have 2 sig figs after that. So we'd want 2 digits after the decimal. Okay, so our pH is 4.77. We're going to skip number 2 because I didn't see any of these buffer solution questions for a base, so we're going to skip that one. And I actually want us, we probably will do number 3 together in class, but let's go down to number 4. So hydrobromic acid, so HBr, which is strong acid, is added to a buffer solution containing acetic acid, CH3COOH. That's our acetic acid, it's weak. And its salt, or its conjugate base, CH3COO minus, okay? Write the net ionic equation for the overall reaction. Okay, now, I'm going to show you more along the lines of the questions that I saw. Instead of the overall that contains like all of this, the way they were phrasing this is they're saying, hey, what is the reaction that demonstrates why the pH isn't changing very much? So this is our buffer, the combination of those things, and we're adding a strong acid. So the strong acid really isn't going to react with the acid, it's going to react with the conjugate base. When an acid or a base is strong and we're looking for a net ionic, you don't have to include the other part that's with it. If it's weak, we do have to include everything. But if it's a strong acid, it's just going to break apart into the H plus and the Br minus, and the Br minus will end up canceling anyways. So we're going to say aqueous, and it's going to react with the base, CH3COO minus, aqueous. Okay, so what you're going to show here is that it's going to create the other part of the buffer, and it always goes either this is going to be creating that or that's going to be creating this. So this hydrogen is actually going to latch on to that base, and so we'll have HCH3COO. Oh, that's funny. We could absolutely write it this way. That wouldn't be marked wrong. The more conventional way, for some reason, with acetic acid is they put the H at the end. And so it's our CH3COOH. And it's making that weak base. So that would be the net ionic for a strong acid being added to this buffer. It makes more of the weak acid that's already in there. Okay. We're going to save number 5 to do in class. And now we've already talked about choosing an indicator. Just a reminder that we want to choose an indicator where it changes color close to, if not at the equivalence point. So if we're trying to choose an indicator, choose which indicator would you use when titrating 0.5 molar acetic acid and sodium hydroxide? And it says the equivalence point occurs at 9.1. So we want a color change to occur at roughly 9.1. And so the 2 potential answers here, we would want either this one, because that's where we get a color change, or it looks like this might also work. This guy might also work on there. And so which one would we choose? I would choose, Alene. Or you could talk about the thymol blue. Like, that would also be an appropriate answer. Phenolphthalene's way more common an indicator, though. Okay, so with that in mind, which indicator would we choose if we're titrating hydrochloric acid with sodium hydroxide? Now, they didn't have to tell you the equivalence point. And the reason why is because, guess what? It's a strong acid and a strong base. And if you have a strong acid and a strong base, the equivalence point should occur at 7. So then we need something that changes color at a pH of 7. So we got 2 good options there. We could either do the phenol red or the prothymol blue. But I think I would prefer the phenol red because that's where we very first start seeing a color change. So I think that would be our better option on this one. Okay, nice. All right. I think that's where we're going to end. Yeah, we're not going to end up doing the space one because I didn't see any questions on that. And then we can consider this one. We have a pH and we have a pKa. And so remember what I was telling you? When our pH is lower than our pKa, so when our pH was lower than our pKa, that means that we had more of the acid in there. Okay? And so when we're comparing that on that last question, what would be in greater concentration? Would it be the acid or would it be the conjugate base? It would be the acid. We'd have a greater concentration of HCN when our pH value is less than our pKa value. Okay, perfect. Hit everything that we needed to. I'll see you all in class.